An understanding of plate tectonics has significantly altered our understanding of the world. The ocean floor has gone from an unknown desert to a fully mapped terrain with mountains, plains, and the deepest canyons on Earth. Both the Rocky Mountains and the Himalayas, created by plate collisions, affect climate worldwide by altering high-level winds, creating snowy windward landscapes and dry downwind deserts and semi-deserts. The changing shape of the seafloor through time shapes ocean currents and equatorial heat carried from the equator to northern landscapes. Barriers thrown up by plate collisions or isolate animal populations or bring them together. An obvious example is that of Southeast Asia, where a barrier has been created between placenta mammals and marsupial mammals by plate tectonic activity on islands that are very close together today. Perhaps of more significance to our current day is learning that investigations of one generation build on a foundation for the discoveries of the next. In our current day downplaying of the scientific process, the danger arises that future generations, as well as our own, might well be limited. If you look at the process of discovery, it is a riveting story of human curiosity and exploration, as well as the institutions that support them. Let us begin the journey of discovery. Scientific understanding is a journey of clarifying a cloudy picture. Discoveries take time and often generations of investigations that consider the questions that came up earlier. Progress in almost all areas of knowledge depend on prior understandings, tools, and questions that have arisen earlier. This video explores how we came to understand our modern world a bit clearer. Who are the people that made the discoveries, and when did they do so? What is it that they discovered? Many ships had sailed the ocean before the 1870s in their quest for exploration and trade, but had learned little about the seafloor during this time. In 1873, a British expedition sponsored by the Royal Society of London set out to change that. Before this expedition, more was known about the surface of the moon than that of the seafloor. The HMS Challenger, a British warship, was retrofitted for scientific work. During the expedition, the ship, the crew, and scientists sailed just over 79,000 miles, cataloged over 4,000 previously unknown species, measured ocean densities, and carried out depth soundings using a long rope. Importantly for this video, they discovered that the mid-Atlantic was shallower in the middle than closer to land. The Challenger expedition also discovered the deepest places in the world, um, and the Challenger Deep at the southern end of the Mariana Trench, a trench far deeper than anything that is known on land. A contradiction occurs when you measure mountain height through time. Why do mountains get higher even as they are being eroded? Mountains are not the only example of land surfaces getting higher. After the weight from the last continental ice sheet was removed, the land that had been depressed under the ice for the last few million years has risen and is still rising or rebounding today. Current research shows that Mount Everest is getting higher by about 2 millimeters a year, related to erosion by rivers near its base. In a similar manner, vast parts of the former heart of the great continental ice sheet that covered a good part of the northern part of North America and Europe is rebounding. These contradictions were addressed by many ancient thinkers on nature, but we've come to understand that the Earth tries to maintain a balance between the densities of rocks under the surface and above the surface. Key contributions came from several scientists. When the term isostasy was coined by Clarence Dutton in 1889, the idea of a balance in the Earth's crust has been explored earlier. George Avery and John Henry Pratt proposed different models to explain this balance in the 1850s. Ultimately, isostasy describes how different parts of the Earth's crust, like mountains and ocean basins, maintain a state of equilibrium by adjusting their depth of penetration into the underlying mantle. We now know that mountains have roots that match or exceed its surface height. To illustrate how this works, the right-hand illustration shows three granite blocks representing small and large mountains that float on the denser mantle, much as two corks floating in water. A certain ratio of the rock is above the surface, and another part is below the surface. All blocks have the same density that is lighter than that of the mantle. If you cut off the top of one of the granite blocks or erode it off, the block of rock will rise so that the same proportion of the block will be above and below the surface as previously. We see similar effects for icebergs and seawater. In Mount Everest's case, the rivers around the mountain are being eroded and the mountain block responds by rising. For formerly glaciated areas, the ice formed over thousands of years slowly depressed the land under it, but melting occurred relatively quickly, removing the weight on the land, and the land is slowly responding. Uh, all this allows us to know there's a plasticity to the earth that in everyday life we think of as solid and unchanging. Importantly, it foreshadows the concept of the asthenosphere, that is a plastic-like layer in the upper mantle that allows for rigid plates of lithosphere to slide about. Existence of isostasy foreshadowed the existence of the asthenosphere. Its presence was first proposed by Reginald Daly in 1914. It was suspected to be present as early as 1926, but the Great Chilean earthquake of May 22, 1960, recorded worldwide, confirmed both its existence and worldwide extent, as seismic waves arrived at seismographic stations around the world. The asthenosphere is a source of basaltic magma rising at ocean ridges and creates a sliding surface for plates to move. The asthenosphere most likely has areas of melting rock, with most others having a plastic-like nature. The separation of the asthenosphere and the rigid lithosphere above, made up of both the crust and upper mantle, is arbitrarily chosen to be 1300 degrees Celsius or 2300 degrees Fahrenheit. Gondwana became famous when Alfred Wegener proposed the concept of continental drift in a 1912 paper, where he noted that South America and Africa would fit nicely together if we just slid them together on a map. Later researchers discovered plants and animals in the southern continents that also fit together like a jigsaw puzzle. Almost all these plants or animals could not have swum across or floated across modern oceans, so they also proposed that these land masses fit together at one time. Most scientists, however, call these early observations circumstantial. Critics of the concept of continental drift could not envision continents sliding about a solid Earth as it was believed to be at the time. There was no smoking gun to prove the concept. In the 1950s, the focus of scientific research turned to exploring the seafloor, about which little was known beyond the HMS Challenger expedition. During the 1950s, systematic ocean deep survey data using modern seismographic equipment was sent to a cartographer at the Lamont Doherty Laboratory in New York, who, while charting this data on a map, discovered that not only was there a mid-ocean chain of mountains, but in the middle of the chain was a rift valley. Furthermore, this rift valley was where the mid-ocean earthquakes were located and new lavas flows. In addition to the new lavas, information emerged showing that the age of the ocean rocks was youngest at these mountains and got older as you moved towards land. Additional discoveries soon followed that allowed for understanding of seafloor spreading. The next slide is about the explorers who made these discoveries. A second cornerstone of plate tectonics is the existence of the asthenosphere. A layer much like the asthenosphere was first proposed in a theoretical paper in 1914 to explain the established observation that mountains seemed to get higher as they were being eroded. But it wasn't until the great Chilean earthquake of May 22, 1960, that geophysical data established the separation of the lithosphere and the asthenosphere in both their existence and extent. By this time, the concepts of seafloor spreading, the existence of the asthenosphere, and plate tectonics was established. As a result, it was a long scientific journey from Wagner's initial crude proposal to a clear and acceptable model of the nature of Earth's outer shell and the mechanism that is modern plate tectonics. Lamont's first director, Maurice Doc Ewing, set out to update the HMS Challenger investigation aboard the research vessel Vima. His team measured ocean depths across millions of miles using sound waves aimed at the seafloor and measuring how long it took for the echoes to reflect back to the ship's detectors. Maria Tharp and her colleague Bruce Hazen made history by turning those depth measurements into detailed maps of the ocean floor. They published the first map of the Atlantic seafloor in 1957 and the first map of the entire world's ocean floor in 1977. Tharp and Hazen's map revealed that seafloor was far from flat and featureless. Instead, they charted underwater mountains, canyons, and a globe-girdling series of mid-ocean ridges that would later help to prove the Earth's continents move through time. Associated with these researchers was the discovery of mid-ocean rifts that was the location of earthquakes and new lava. Harry Hess proposed the seafloor spreading hypothesis in 1960 and published this in 1962. The term spreading of the seafloor was introduced by geophysicist Robert S. Dietz in 1961. According to Hess, seafloor was created in mid-ocean ridges by the convection of the Earth's mantle, pushing and spreading the older crust away from the ridge. Geophysicist Frederick John Vine and the Canadian geologist Lawrence W. Morley independently realized that Hess's seafloor spreading theory was correct. then the rocks surrounding the mid-ocean ridges should show symmetrical patterns of magnetic reversals using newly collected magnetic surveys. Both of Morley's letters to Nature in February 1963 and the Journal of Geophysical Research in April 1963 were rejected. Hence, Vine and his PhD advisor at Cambridge University, Drummond Hoy Matthews, were the first to publish the theory in September 1963. Some colleagues were skeptical of the hypothesis because of the numerous assumptions made: C4 spreading, geomagnetic reversals, and remnant magnetism, all hypotheses that were still not widely accepted. During the Pacific exploration in 1966, then Lamont grad student Walter Pittman made a discovery on the ship, the Eltenian, that had been towing a magnetometer behind it, catching the magnetic alignment of the rocks on the seafloor. Back at Lamont, while looking at the recordings captured while the ship crossed a mid-ocean ridge, Pittman realized that the pattern of magnetic reversals was symmetrical, with the mid-ocean ridge as the center point. He almost instantly knew he was seeing evidence of seafloor spreading, that the seafloor formed from lava at the mid-ocean ridges and spread outward from there. This discovery verified the Vine-Matthews-Morley hypothesis. The illustration shows the mysterious stripes of magnetism that mirror image on either side of an ocean ridge. These stripes represent the orientation of Earth's magnetic field when lava erupts at a ridge and magnetic minerals orient parallel to the magnetic field and then freeze in that orientation as the lava cools. As the seafloor spreads, the lava is split into two mirror images, as is the magnetism locked in. With the churning of the Earth's core, the magnetic fields reverse through time, and this too is reflected in the magnetic stripes. Iceland is a unique place where a mid-ocean ridge and spreading center sit on land. In the slide, the North American lithospheric plate sits on the left, and the European lithospheric plate sits on the right. These plates are separated by a narrow rift or fault that is the mid-ocean spreading center. The rift is a broad zone, several hundreds of meters wide, but this is the center of it. Through time, average plate spreading rates have varied from about 0 to 15 centimeters per year, although most current plates spread at about 1 centimeter per year. In Iceland, the current spreading rate is about 1 centimeter or 0.4 inches a year. On April 21, 1979, an expedition by both French and American scientists carried out a deep dive aboard the submersible Alvin. They were going to check out the Mid-Atlantic Spreading Center. On April 21, 1979, Alvin dove in search of hydrothermal vents. Bill Normack of the U.S. Geological Survey and Thierry Juteau, a French volcanologist, were the scientific observers. The pilot of the submersible was Dudley Foster. He followed a trail of white clams on the seafloor. By now, the researchers knew they would lead to vents that were seen in an earlier dive by the French team. Suddenly, the scientists came upon something no humans had ever seen before. They saw a tall spire of rock, about 6 feet tall, sticking out of the seafloor. A jet of black fluid spewed out the top like smoke out of a chimney. Foster said it looked like the smoke belching out of the smokestack of a steaming locomotive. These smoking hydrothermal vents carry an abundance of minerals that are a source of chemicals that in ancient seafloors are now on land and create mineral deposits. Organisms like tube worms, mussels, and shrimp thrive in these extreme conditions, relying on bacteria for food. Northern New England's coastal rocks, as well as a good part of the northern continents, form south of the equator. To understand how they were transported northward and came to be on coastal North America and northern Europe, it's important to look at plate tectonics. We now know that similar transportation of exotic or foreign terrains has taken place on both the west coast and east coast of North America, and looking back in time for the entire continent. So how has this been accomplished? Lithospheric plates are plates of rock that include both surface rocks and extend downward beneath the surface for many miles. The present-day arrangement of lithospheric plates is shown on the map. There are 7 major plates separated by either mid-ocean ridges where new magma comes to the surface, and then a cooling plate moves away from the ridge. Mid-ocean ridges, such as the Mid-Atlantic Ridge, show red arrows pointing away from the ridge. These ridges are some of the highest places on the planet, but we don't see them as they're covered by water. New ocean floor is formed here, and the plate moves away. A good example to explore is the smaller Nazca Plate west of South America in the Pacific. As the plate moves away from the ridge towards South America, it cools and sinks, and eventually it sinks or is subducted under South America. As the plate is subducted, it partially melts. Partial melting occurs in the descending plate and then rises as it is of a lighter density than the continental rock around and above it. When it reaches the surface, it forms a chain of mountains inland from the coast that is the Andes mountain range. In detail, the mid-ocean ridge is offset by transform faults that are breaks in the lithosphere at right angles to the ridge. These transform faults appear on the maps by Maria Tharp and her colleague Bruce Hazen. These faults accommodate different movement amounts and rates on either side of the mid-ocean ridge and along different sections of the rift that is often curved. One transform fault that stands out as it relates to California is that of the mid-Baja California spreading center. This also has transform faults, one of which extends through California, where it's called the San Andreas Fault, that was responsible for the destructive April 18, 1906 earthquake in San Francisco and is still active today. Modern day rifting is perhaps best shown in East Africa in its famous Rift Valley. Well-known waterways in advanced parts of the rift include the Red Sea and the Gulf of Aden. Inland, the Nubian Plate to the west is splitting from the Victorian Plate and the Somali Plate to the east. The left-hand diagram shows rifting in the region, with the right-hand photograph showing the location of the newest rifting inland by a chain of lakes in an arc shape. Volcanoes are formed um, in the adjacent to the rift with a popular climbing objective, Kilimanjaro, sitting south in Kenya on this rift. At the edge of an ocean basin, heavy basaltic rocks dive under lighter granitic rocks of the continents. As these plates dive, they're said to be subducted. In the process, friction produces earthquakes. At depth, partial melting produces melts that make their way to the surface. So inland, adjacent to the subduction zones, you often find volcanoes such as the Andes, the Cascades, the Aleutians, and so on. What drives tectonic systems? It turns out that heat and gravity are fundamental to the process. Lithospheric plates are part of a planetary system of thermal conduction. The energy source for plate tectonics is Earth's internal heat, while the forces moving the plates are ridge push and slab pull gravity forces. It was once thought that mantle convection could drive plate tectonics. Early textbooks showed mantle convection cells like in a beaker of hot liquid on a Bunsen burner, pushing plates along from below. Convection in the mantle certainly plays a role, but doesn't explain how some plates move faster than the convection currents beneath them. What would cause that? Current dynamic models have plates moving as part of a gravity-driven convection system that pushes young hot plates away from spreading ridges and pulls old cold plates down into the subduction zones. Around the edge of the Pacific Ocean, adjacent to a subduction zone, is the Ring of Fire volcanic zone. We will have a look at that next. In North America, the volcanic mountains of the Cascades and north into the Canadian west coast lie on the western margin of the North American lithospheric plate, where smaller oceanic plates are being subducted and partially melted underneath the west coast of the United States and Canada. In the Cascades, Mount Baker, Mount Rainier, Mount Adams, Crater Lake, and Mount St. Helens, as well as those of the British Columbia Range, are all formed in this way. The Juan de Fuca Plate, the Explorer Plate, and the Gorda Plate um, in Northern California were once part of a much larger ancient Farallon Plate that played an important role in the formation of the Rocky Mountains of the central United States. These volcanoes are high enough to be covered in snow and form mountain glaciers. On the west coast, these are popular recreational areas for climbing that draw local and worldwide recreationalists. These volcanoes have real and potential danger to the Pacific Northwest population. The explosion of Mount St. Helens in 1980 seriously affected the Northwest, sending ash into the atmosphere, creating mud flows composed of eruptive ash and water melted from the glacier called lahars, and killed 57 people while destroying at least 27 bridges and 200 homes. The ash closed airports and auto travel throughout the Pacific Northwest. Similar volcanic explosions in Iceland and Indonesia disturbed air flights over wide areas among similar events in the last 10 years. A current watch exists on Mount Spur in Alaska that has the possibility of explosive ash disrupting air travel over the Pacific Northwest as well as Alaska. Tectonic processes release energy at plate boundaries that control the process of mineral deposition and concentrate metals until they are worth mining. They also help in place minerals in mineral fields that differ for different types of plate boundaries. An understanding of plate processes has allowed reconstruction of fragmented continents that is used to explore for new mineral deposits. Mineral deposits may well be associated with different types of plate tectonic boundaries. These include divergent boundaries where plates separate, convergent island arc systems, and plate-to-plate collisions. Plate collisions sometimes trap and metamorphose ancient seafloors on land. In addition, there are sedimentary basins associated with magnetic zones formed through the collisions. These processes concentrate sulfides, copper, zinc, gold, silver, chromium, lead, manganese, cobalt, nickel, bismuth, lithium, tungsten, and tin, among others. These metals may be carried and concentrated by hot pressurized liquid, forming valuable deposits. The process of plate tectonics and the wealth created by them has been and remains critical to ancient as well as modern societies. Understanding the distribution, collisions, mountain belts formed, and seafloor formation and creation is essential to understanding our world, its past, and even our future as an industrialized society. Plate tectonics, taken to its logical limit, implies that as one lithospheric plate moves away from another, it might crash into another plate coming from another direction. Research shows that this has indeed happened more often than not, and eventually all the land masses of Earth come together into one big landmass, our supercontinent. Research recognizes three of these supercontinents that are definite, going back more than a billion years, with the possibility of more supercontinents further back in time. Supercontinents form, split up into large chunks, and separated into smaller chunks and slivers of land. Today, our largest landmass is that of the combined Africa, Europe, and Asia, making up about 57% of land masses. The three definite supercontinents are those of Columbia, Rodinia, and Pangaea, shown in the illustration. The oldest of the definite supercontinents is Columbia, named because basaltic lava flows in eastern India are connected to those of the Columbia Plateau in Washington state. These basaltic outflows are some of the largest that has occurred in Earth history. At 1 billion years, the supercontinent Rodinia formed. It later broke up to produce both southern as well as northern plates and landmasses. It is possible that Camden area rocks originated here, although one of the pieces formed from the breakup is the more likely place of origin. From this breakup, the largest southern piece was Gondwana, created about 530 million years ago. Later continents again came together to form the supercontinent Pangaea when Gondwana moved northward to collide with northern landmasses. Gondwana plays an important part in our story since this landmass is where Camden main area rocks most likely came from. Today's present-day Atlantic Ocean began to form when Pangaea broke up, somewhere on the order of 170 million years ago. With this quick rundown of the movement of continents through time, we will focus on Gondwana since that is where Camden Age rocks were created, somewhere around 500 million years ago. Ancestral North America consist of a core of very old rocks that has been in existence for several billion years. This core is called the craton, meaning that it has been stable for a long time. However, this stability has recently been called into question, as recent seismic data indicates that the craton is slowly peeling off from underneath and sinking. The craton is centered around the Superior Province and its rocks in Canada, with belts of rocks added to the side during the creation of supercontinents and assembling small pieces. These pieces in turn were derived from earlier collisions. The most northeastern state, Maine, consists of younger belts of rocks created from collisions with island systems or microcontinents, with the youngest two making up central Maine west of the Norumbega Fault and the coastal volcanic belt, which is composed of exotic terrains that broke from Gondwana. A feature of our planet is that continents form, break apart, and move with new oceans forming. Following this introduction as to how we came to accept plate tectonics, what does the distribution of plates and terrains that they created look like in different parts of the world? On our planet, the creation of mountains and elevation changes creates barriers to animal migrations and worldwide wind patterns. Changes in the ocean basin floor and resulting changes in water currents affect worldwide heat distribution. All of these affect animal adaptation and evolution to newly created environments through time. Slides to illustrate this follow. Alaska is an example of how the west and east coast of ancestral North America were expanded by exotic terrains that are island arcs and microcontinents accreted to Laurentia, or ancestral North America. In the illustration, the blue areas represent older portions of ancestral North America, or Laurentia, that were accreted to or added to later in geologic time. Similar accretion maps exist for the U.S. Pacific Northwest and California, as well as the east coast of the U.S. An interesting observation is that Denali, topping out at 20,300 feet, is higher in elevation than any of the Rocky Mountains that top out around 15,000 feet. Denali lies inside a 19-degree restraining band in the active Denali Fault system that is moving at about 7 millimeters per year, providing a tectonic and structural driver for ongoing rock uplift. High elevation differences of Denali are also due in part to its granitic rock type and low fracture density relatively to adjacent sediments that have been metamorphosed. Unique climate conditions at high elevations lead to low erosion rates at elevation that also contribute to the growth of relief. That is the difference between elevations at the top and the bottom of the mountain. The Rocky Mountains, currently in mid-continent, present something of an enigma. How did a mountain range come to be far from a plate boundary? Since we know that most mountain building events occur at the edges of a plate. Current thinking is that the Rocky Mountains are the product of complex plate processes. Today's small plates off the Pacific Northwest and extending down into California are the remnants of an older, much larger plate named the Farallon Plate. When the west coast of North America was near Utah, the Farallon Plate changed from a steeply diving plate as most are, to a shallow diving plate so as to reach further inland. This led to a mountain building period named the Laramide orogeny that was active from 80 million years ago to 50 to 35 million years ago. This mountain building period not only created the high peaks of the Rockies, but is also responsible for the creation of the Basin and Range province. The mountains receive abundant rainfall and snow, whereas the plains east of the mountains lie in the rain shadow. The details of the formation of the Rockies are complex and beyond complete explanation here. But online is an abundance of literature and videos if you wish to understand this topic further. A good place to start is by exploring and searching for the Laramide orogeny in the Farallon Plate. The east coast of Laurentia shows a similar pattern of accretion of island arcs and microcontinents through time, although these are generally older than most of the exotic terrains of the west coast. In the diagram, the older stable craton of Laurentia is shown in blue. The exotic terrains of the Gander terrain of central Maine and the Avalon terrain of coastal Maine are as indicated. In southern Nova Scotia, the Nagooma terrain accreted to the Avalon terrain. In the southern Appalachians, the Caroline terrain accreted between Georgia and Virginia. To explore further, look for the topics of the Sklenic orogeny, the Acadian orogeny, and the culminating Allegheny orogeny in the southern Appalachians. My other video on YouTube entitled Coastal Maine's Origins is indicated on the slide on your screen. Europe has been built by multiple plate interactions, focusing here on the alpine regions. The alpine orogeny or mountain building was caused by the African continent, the Arabian Peninsula, the Indian subcontinent, and the Crimean plate colliding with Eurasia in the north. Convergent movements between the African, Arabian, and Indian plates from the south and the Eurasian plates and the Anatolian subplate from the north, as well as many smaller microplates, had already begun during the early Cretaceous period from 145 to 166 million years ago. But the major phases of mountain building began during the Paleocene from 66 to 56 million years to the Eocene 56 to 34 million years ago. Plate processes continue today in some of the alpine, Himalayan, orogenic belts, mountain ranges. As an example of the tremendous forces involved in these plate tectonic collisions, an insert diagram of the Matterhorn shows that the peak was originally African rock deposited at the modern-day boundary of Switzerland and Italy, where it sits on former ocean bottom rocks. Plate tectonics around the world has changed land nature, distribution, elevation, climate, and wealth, and is still doing so today. Offshore Asian creation of land island systems, tsunamis created by undersea plate movements, explosive volcanism, and mineral wealth of the region are all relevant today. The illustration here shows the complex currently active plates off of northern and Southeast Asia, including Japan, Taiwan, the Philippines, and Indonesia. Associated with the plates are active volcanoes and earthquakes that have pronounced effects worldwide from creating tsunamis and volcanic explosions. Is an example for the potential of worldwide influence and lingering influence originating from plate movements is the explosion on Mount Tambora, April 10th, 1815, in present-day Indonesia. This explosion was among the greatest volcanic explosions that Earth has experienced. The explosion put an estimated 24 million cubic miles of gases and dust and 60 megatons of sulfur into the lower and upper atmosphere. These materials reflect sunlight back to space, cooling the Earth, and were distributed by high-level winds worldwide. As a result, this led to the year without a summer in 1816. During this summer, the climate was so cold in northern Europe and North America, there were crop failures bringing about hunger and migrations. As an example, in Maine, where I lived half my life, there was snow each month of the summer, which was disastrous to life led by subsistence farming. This was followed in 1825 by the Erie Canal completion and the discovery of gold in 1848 that led to an outmigration from the state that was not reversed till the 1970s back to the land movement. Tsunamis are particularly dangerous to Southeast Asian populations and occur every few years due to ocean floor plate movements that displace seawater upward. This bulging seawater spreads outward, creating waves that become tsunamis that build in height as they impact land. The slide shows the results of a 2005 particularly destructive tsunami that impacted Sumatra. Similar tsunamis have impacted Thailand in recent years. India separated from the African portion of Gondwana about 110 million years ago and began a journey northward to Asia, where it started its collision about 10 million years ago. It is still actively attempting to move northward, with Asia resisting. In the process of collision, many different faults, basins, and junctions have formed and are active today. In the process, the North Indian Basin, the Himalayan mountain range, and Tibetan Plateau have formed. Human populations living here have adapted to the average 14,500-foot Tibetan Plateau and its relatively thin atmosphere. Lhasa, the largest city, lies at 11,999 feet, which is far higher than the Denver, Colorado, sitting at 5,279 feet, that new dwellers often have difficulty adapting to its elevation. In western China's Sichuan province, major cities are impacted by destructive earthquakes associated with the breaks or fault movements formed during this collision. These faults were formed as India pushed and is pushing against Asia. In the particularly destructive earthquake of 2008, 69,000 people died and many buildings in the province were severely damaged. The illustration shows a school in Sichuan that was destroyed during this particular earthquake. The enigmatic Wallace Line. The Wallace Line in Southeast Asia is a biogeographical barrier first mapped out in 1863. by British naturalist and explorer Alfred Russel Wallace and later modified by Weber. These lines are imaginary dividers marking the differences between species found in Australia and New Guinea and Southeast Asia. This line, although imaginary, is a real barrier to animal migration. It is especially apparent when considering the difference in mammals between the two regions. South and east of the line, marsupials and monotremes are found, unlike the placenta mammals found north and west of it. Researchers now believe that the distribution of species across the Wallace Line was caused by extreme landform and sea currents induced climate changes resulting from plate tectonic activity around 35 million years ago, when Australia broke away from Antarctica and crashed into Asia, giving birth to the Malay archipelago. This presentation has two themes. First is the long process of scientific investigations, where the advances of one generation enable those of the next in bringing about new knowledge. Second is the impact that plate movement, past and present, have in our lives through landform and climate changes, natural hazards, and mineral wealth. Past, present, and future societies depend on this information. In 50 million years, there is a real possibility that a new supercontinent will form, bringing about all land masses of Earth together, placing currently widely separated plants, animals, and humans into proximity. How will that play out? Will mankind still be present and dominate the planet? How will animal populations change? Will we learn to live in harmony with each other when living side by side? Today we live in a time where fear and rejection of human differences, as well as science-based learning, is discounted. What price will future generations pay losing out on opportunities to expand both human and scientific learning today?